Hello everyone, welcome to this video. So today we will see one Simscape based example for modeling and battery pack consisting of a faulty cell. So it was developed by MathWorks. So to open the model, we need to run one command in our command window, that is ssc underscore lithium underscore battery underscore with underscore fault. So once we write this command uh, over our command window, MATLAB command window, and we click enter, so automatically this model will open in a Simulink window. We can see this. So basically, this example shows how to simulate a battery pack that consisted of multiple series connected cells in an efficient manner. It also shows how a fault can be introduced into one of the cells to see the impact of battery performance and cell temperature. For efficiency, identical series connected cells are not just simply modeled by connecting cells models in series. Instead, a single cell is used and the terminal voltage scaled up by the number of cells. The fault here is represented by the changing the parameters for this cell to introduce a fault subsystem. So by reducing both capacity open circuit voltage and increasing the resistance value. So we will come to this. So basically this is the model where we can see total 1 to 9, then 10 and 20. So total 20 cells are connected in series to make a battery pack. Here we can see this is the ambient temperature source. If we just double click on it, you can see here one variable is written, t underscore init. We will come to this variable. So what data is stored under this variable and others variable also, we will see that. Then a thermal subsystem has been built here to introduce the thermal effect over the cells, over the battery pack. So this is a convection ambient heat transfer. Then this is also same here. This is the basically the conduction. If we just okay, if we just you can see basically this is the conduction heat transfer block. So from the ambient through the convection process, it is going to be transferred over the cells, as well as the temperature is increasing over the cells. So through conduction process, the temperature is also exchanging between the cells of the battery pack. Here, if we just, so here you can see 1 to 9 cells are connected in series. Then 10th cell is the faulty cell where we have introduced some parameters to introduce the faulty subsystem. We will come to this, and here the another 11 to 20 cells are connected. So total 20 cells are connected in series. And through cyclic charging and discharging profile, this battery pack is cyclically charging and discharging. We will see this. So to open this battery pack, so first 9 cells, if we just uh, click on this arrow, this type of subsystem will open, where this is the thermal model for the battery for this 9 batteries. So where heat is being uh, transferred to this battery, where there is one temperature sensor that is measuring the temperature difference between the ambient temperature and a reference. So here one thermal reference is also connected, and this is the battery thermal mass is connected here. So this is the basically the battery model. So if we just double click on it, this battery subsystem will open. So under this, the battery is designed in reference to the Thevenin's 1RC equivalent circuit model, where this is the open circuit voltage uh, subsystem. Then uh, internal resistance R0 is connected with series, and also uh, the internal another resistance R1 and capacitance that are connected parallel to each other are connected in series with this circuit. So basically this parallel connected resistance and capacitance are the major reason for introducing the dynamic behavior over the cell. So if we just double click on any of this block, we can see, so based on some experimental data for capacity, uh, voltage, SOC, temperature. So based on those experimental data, a lookup table has been created, and those lookup table data are being fed to this model. Similarly, for this C1 block also, uh, here you can see lookup table data has been fed to here. And if we want to go for the details of this model, like how this model has been built, we can go to the source code option under this description tab. If we just click here, it will refer to our code. So this is the background code for those blocks. So for each blocks, there are some different background codes. So where the logics has been written, how mathematically the parameters and other things are being calculated. Now, let me just close this. If I just come to this model again, if I just go back here. So here you can see this is the controlled voltage source and this is the voltage sensor that are connected. Okay. Now, similarly, if I just, so this 10th cell is the faulty cell. If I just go here, I just click here, you can see some parameters. So here, similarly for this one also, we can specify how many cells are connected in series. So here 9 cells, first 9 cells are connected in series. So it is written number of series connected cells as 9. Then initial cell charge deflect, the charge inside the cell initial charge has been stored under a variable called QE underscore init. You can see the value as well, 15.684. Then this is the initial temperature that we have seen under this ambient temperature as well. Then under this electrical parameters, we can see all the parameters like capacity lookup table data, open circuit voltage lookup table data, then internal resistance lookup table data, then R1 cell resistance, that is the parallel connected resistance lookup table data, parallel connected capacitance lookup table data, then thermal lookup table data is present. Similarly, all the other lookup table data are also present here. Okay. If I just go for this faulty cell, 10th position faulty cell, we can see here the capacity has been factorized with a factor of 0.95. So capacity has been decreased for 5%. Now it is 95% of the other cells for compared to the healthy cells. Similarly, here open circuit voltage also reduced with a factor of 0.9. Then internal resistance has been increased for 5 times by multiplying the data with 5. Then also the dynamic resistance and capacitance data is also factorized. So by introducing these factors, these values, we are introducing a faulty characteristics under this battery. Now, if I just come to this 11 to 20 cells, these are again healthy cells. The characteristics is same as like this first 9 cells. So we can see the data, lookup table data has been fed. Here we can change the number. So if we want to make this battery pack for more numbers of series connected cells, we can increase the numbers here. And also we can connect these batteries in parallelly to make a big battery pack for parallel connected battery packs as well. You can make this. Now, if you want to see the lookup table data, so all the lookup table data has been loaded under our MATLAB workspace. So similar, suppose we can open the C1 lookup table data, that is the dynamic capacitance data. If I just double click on it, you can see the data here. So this data basically in term of SOC and temperature. So here this SOC, we can see for this SOC, this is basically our data for 0%, 10%, 25%, 50%, 75%, 90%, and 100%. So total 7 data points, 7 rows are present. And for temperature, three columns you can see are present. So in term of matrix, so all the other lookup table data like C1 LUT, so 7 cross 3, that means 21. So 21 data has been created here. So first one, if I just check here, so first one, the row value for the SOC was 0%. So when SOC is 0%, and temperature is 278.15 Kelvin. At that point, the C1 value is 1.91. Similarly, when temperature is 293.15 and capacity and the SOC is 0%, then the then the C1 lookup table value is 12,447. Like this, if we just see here, this is the for 10% of SOC and temperature of 278.15 Kelvin. So based on this, this experimental data has been plotted here to make a lookup table data. Okay. Now, if we just come here, we can see as this model is being developed by MathWorks, so copyright is there, but we can use this for our learning purpose, and as well as for experimental purpose. We can add several cells in parallel also to make a more complicated battery pack. Now, if I just run this model, so it will take some time. So once run, we can see if we just open this. So basically the first data is for 10th cell temperature, and this uh, last go to block is for 20th number of cell. Now we just see the temperature uh, behavior for those two cells. One is healthy cell and another one is faulty cell. So this healthy cell temperature is plotted in term of pink or purple color. We can see the temperature is behaving like this. The maximum temperature it is going for 320 Kelvin, where the faulty cell temperature is rising up to 330, more than 330 Kelvin. So we can see some faulty or abnormalities over the faulty cell. Now, if we just open this subsystem, this is the T subsystem. So under this, so based on the temperature sensor, those temperature are being collected over the go-to block. Then with the help of a from block, this is being shown over the scope. Now we can add here one temperature sensor as well for the uh, first 9 cells. So what I have done, I have just copied this subsystem for temperature measurement, and I am connecting over here. So I have connected this. Now let me just go here and I can change the name. So let me keep the name as 9, and we can keep the tag visibility as global, because once we keep any go-to block under a subsystem, then if we don't select to global, if we just make it to local, then it will not be readable outside the subsystem using the from block. So to for visibility, we can make it to global so that it can be visible outer of the subsystem as well. So here I have make it name of T cell line. Now if I just take a from block, so here this is the from block. Now let me just change the name. So if I just open this, double click this, we can see all the go-to blocks that are present over the model. It is showing here. So this is for T cell line. I'm selecting this and I'm clicking apply and OK. Now I can connect this here. So let me connect this. Let me just make it a small size. Okay. Now I can connect it here. if I just run this model, let me just, yeah. Now, if I just save this, okay. Now, if I just run this model, so it has run. Now, we can see there are 3 lines. So as first 9 cells and the last 20, cell 20 and the 9, okay, let me just give the name here so that it can come in term of legend. So I'm just naming as cell 9. Now, if I just run this model again, if I just double click it, we can see here the legend is present. So the color is yellow, and so there are 2 healthy cells. We can consider 2 module of healthy cells. One is for cell 9 and another one is cell 20. So those 2 data in yellow color and uh, in green color we can say. So as the data is for healthy cells, so the data is almost same, we can see. But as the number 10 cell is the faulty one, that's why it is showing abnormalities over the temperature. Now, if we just want to check the capacity, how the capacity is being varying over the cyclic charge and discharge profile. So if we just want to see what we can do, we can just open the subsystem, and inside this battery, this is the SOC signal that is going for further calculation over the different subsystem for C1, R1 and R0. So we can connect here, go to block. We can connect here a go to block, and as this is comes under Simscape library, so it's not possible to connect directly with the Simulink library block, this go to block. So we need to use a PH to Simulink converter to convert this signal in term of Simulink signal so that it can be readable over the Simulink block. So now I can connect it. Okay, now I have connected it. Now just let me just change the name. We can give the name like SOC. So this was for the first 9 cells, right? So we can give the name like SOC underscore 9, and we can change the tag visibility to global. We can click apply and OK. Now for other batteries as well, I want to connect this and check the SOC behavior. So I will simply copy this thing and I can go back for the other battery. So this is the faulty one. I can go here and here I can just paste that and I can connect it. So one thing I need to remember whenever I'm copy or pasting anything, I need to remember to change the name. So it's the faulty one. So I have changed this to SOC 10. Now I can come to the 21. Yes, here I can connect it here as well. I can connect here. So this is total SOC signal. We can connect this signal to here as well, or here as well, or any other here as well. Wherever the SOC signal is going, we can connect it with there. Now let me change the name to SOC 20. So I can click apply and OK. So all the go-to block for SOC measurement has been setted. Now I need to take a scope. Now I need to take a marks, or I can connect it individually as well. Now I can connect it here. Then let me take a from block to feed the stored signal into the scope. So let me just, okay, let me just copy this another time. Yeah. Now I can change the name. So once I click this arrow, it will suggest all the go-to block for all the go-to block that are present. So we have already used this T cell 9, 10, and 20, but we need to use this SOC 9 first. Can connect it here. Okay, I can double click on it and change the number of inputs. So there are 3 inputs here. So I'm just changing to 3 and clicking apply and okay. Then this one, I will set it for SOC 10. I click apply and okay. Now this one is for SOC 20. I'll go here. I will select this one. I click apply. So once I am clicking apply, as the go-to block for this from block is present, so it is showing the source of this. If I just click here, so it will redirect me to that go-to block. Once I name all the things properly, I have connected this. Now if I just run this, it has run, and once we open the scope, we can see the characteristics. So as I don't give the name for this signal, so it's not showing any legend value, any legend. So let me just name this as SOC 9. This one is for SOC 10, and this one is for SOC 20. Now I have named it. It will show me the legend. I have clicked run, so it got run. Now if I just open this, here inside this view option, you can turn on the legend. Now, so green line is just overlapping over this red line. That's why it's not clearly visible, but it's overlapping. As the SOC 9 characteristics and SOC 2 characteristics is same, that's why it's getting overlapped. Similarly, for temperature characteristics as well, we have seen those 2 type of lines was overlapping. But here we can see for the faulty cell, for the SOC 10, the capacity is not going beyond this limit. Whereas for the healthy cells, the capacity is going, capacity increasing further than this. So as we have changed the capacity parameters and we have added some gain value, that's why it's behaving like a faulty cell and the characteristics is not matching as the regular cell. So it's very crucial to identify a faulty cell in a physical system of a battery pack. Whenever there is a battery pack whenever there is a battery pack and a faulty cell is present over there, so it will directly affect the overall performance of the battery pack. As here we can see for the faulty cell, the capacity is decreased, capacity got decreased, the temperature is increasing beyond the healthy cell temperature level. So it will directly affect the battery pack performance. The battery pack usable capacity will decrease, the temperature management can be failed. So these type of issues can happen. So it's very important to identify the faulty cell and replace it with a healthy cell. So this is the model where we can run a battery pack consisted of a faulty cell, where we can connect other faulty cells, other healthy cells to make a more complicated battery pack. So thank you. If you got any questions, please feel free to ask.